Hi, everybody. We're going to go over angular kinetics this week, coming to you from my lovely basement. It's about one of the quietest places in my house, although you might hear some footfalls upstairs or my dog barking every now and then. Pay no attention, stay focused, and we'll get through it. All right? So let's go ahead and jump in. Just FYI, Zoom, I'm recording on Zoom and it has a lot of features, so I might try and explore them while I'm doing the lecture. It's my first time trying it, so if it takes me a minute or two, just kind of fast forward if you need to. Learning objectives for this chapter, review these if we're getting close to an exam. They're the big hitters in the chapter. And if you can understand most of these, you should be okay. Combine that with the study guide and you're good to go. All right, so let's start with the first concept of the lecture. What is center of gravity? Center of gravity can kind of be an abstract concept. It's not an actual structure in the human body, right? So it's just this floating imaginary point in the human body, but it's really important. And I think one of the easiest ways to explain center of gravity is to not use the human body at first, and to use something a little bit simpler. So let me scoot back a little bit. And so what I have here is just a foam roller, okay? And it's uniform, meaning it's the same throughout. It doesn't change its shape from one end to the other. And so I'm gonna find the balance point here. All right, I found the balance point. And it's right in the middle. And that is the center of gravity, right? So what that means is gravity is pressing down all over this place. But the point at which it is centralized and balanced is this center right here, okay? That's because every single part of the mass of this foam roller is now balanced on this point. And I can do that because the structure of this specific foam roller is designed that way. If I have a lot of foam rollers. If I had a different foam roller, it would be different because this is shaped differently. Let's see if I can do it. Can I get it? And we're close. I'm using a couple fingers here, but it's a much longer foam roller, okay? But it's relatively balanced. Right? Not the same balance point, but pretty similar right in the center as the last one. Now, what if I start to add weight to one side of it? What if I take one of these wrist straps here, kind of put it off to the side there? And then what if I start to do this? Oh, we get a tipping. Okay, so what happened there? What happened there was that when I start to stack my wrist straps off to one side, the center of gravity is no longer where my hand is. It's actually started to move this way, right, towards the new weight that I've added. So in order to balance now, I would have to move my hand closer to the weight, right, so that I could balance it. If I move farther away, it's just going to tip even more. So I got to find that perfect spot. Can I find it? I sort of got it. Nope. I think I got it. I got it. Good. All right. So the same thing happens in the human body. And the human body is much more complex. We have a center of gravity that when we're just standing upright, you would say that it's about right where your belly button is, just like in this first picture down here below. But what happens when we start moving? Well, we have this central point and everything is balanced around it. But then if we start moving our body, which the different parts of my body have mass, they have a weight to them. And if I start moving them away from the body, that's going to change the center of gravity. So let me make my screen a little bit bigger for you guys. Right, so if we look at, if we take an experiment, and I would encourage you guys to do this yourself, right? If we're standing here and all of a sudden, well, my center of gravity is balanced right now. All the parts of my body are balanced around this central point right here. Nothing is changing. But then what if I take one of my my legs, and your legs are the heaviest appendage on your body, much heavier than your arms, even heavier than your head, right? So if I take my whole leg and I start to move it out this way, right, what's going to happen? Well, just like in the foam roller, my center of gravity is going to start moving this way. And if I don't want to fall over, what do I have to do? Well, I have to lean. And what happens then is everything is now balanced. I'm cool again. Now, if I were someone who is like a gymnast or who was just a little bit more flexible, I might be able to put my leg out, and if I have really, really good core control and postural control, I could probably, lift my leg all the way up, and my center of gravity might start to shift that way. But if you are very, very strong, like a gymnast would be, you would be able to control and overcome that force of rotation that's going to want to pull you over. Just your position of your center of gravity is really, really important when we start talking about whether or not things are rotating around the human body or on the human body, or if the human body itself is the thing doing the rotating. Okay, so what is moment of inertia, right? What is moment of inertia? Well, we talked about inertia before, and it is force equals mass times acceleration, right? I lose my mouse sometimes, so sorry about that. Force equals mass times acceleration, right? That describes inertia. Linear inertia, straight line inertia, not rotating inertia. And so when we talk about the word inertia, what that means is the resistance to movement. So if something has a much larger mass, and look at the equation, if something has a much larger mass, it's going to require a really large force to move that mass or accelerate that mass. So that's inertia, linear inertia, easy. That's one of Newton's laws. So what about this moment of inertia? It's basically the angular description of inertia. How easy or hard is it to rotate something around a central axis? So that axis could be your elbow, right? It could be your head on your vertical axis. It could be your body, right? It could be lots of things. It could be how easy or hard is it to rotate your leg around your hip, right? So moment of inertia is just angular inertia. But it does have a couple different components to it than linear inertia, and we're going to take a look at that right now. Okay, so we have something like this this baseball bat here, right? And if you can see this thing, sorry about that, we'll move that out of the way. So we have a baseball bat, right? And baseball bat is not uniform. So it's not like my foam roller here, because my foam roller is the same width all the way through. A baseball bat is skinnier at one end and fatter at another. So how easy is it to rotate the baseball bat, right? How easy is it to rotate it? So if we had a baseball bat and we held it right at the end there, I don't think I have anything around here that's like a baseball bat, but you can imagine that we would hold it and we would rotate it, right? Just around an axis that we create with our wrists. So how easy or hard is it to rotate an object? And that object can be a body part or it could be a baseball bat. That depends, how easy or hard it is to rotate depends on a couple different things. And these factors describe angular inertia or moment of inertia. Moment of inertia is just angular inertia, right? So how easy or hard is it to swing this baseball bat? The first thing that we are going to talk about is the mass. Oops, let's go back. My bad. First thing we're going to talk about is, I don't know what's happening, guys. Sorry. User error, user error. I'm trying to draw something on here. There we go. There we go. So let's talk about mass. When you look at the baseball bat, all right, and we consider the mass of the baseball bat, we have to consider how the mass is distributed. And on a baseball bat, you can see that at one end it's skinny and the other end it's fat. And that matters, right? So your book also describes it as the particles, the product of each particle of mass. All that matters is how are things spread out on the thing that we're talking about. So if we're talking about my forearm, if we add up all the particles of mass, how are the particles of mass in my forearm spread out? Well, it's kind of like a baseball bat. It starts out skinny and then it widens out at the end, right? So that's mass. We have to consider how the mass is organized, right? What about the radius, right? So that's the second thing we have to figure out. I've lost my mouse again. I feel like this might happen a few times. Sorry. There. There it is. The second thing we'll talk about is radius of rotation. Okay? And the radius of rotation is how far away is this mass that we're talking about, how far away is the mass from the axis of rotation? So on a baseball bat, when we start to get to the fatter end of, when we start to get to the big fat end of the baseball bat, that mass is actually farther away from the axis of rotation. So now we have an object like a baseball bat that has more mass at one end than it does at the other, right? It has more mass at one end than it does at the other. And at that end where it's fatter, it's further away from the axis of rotation. So that actually sets up the baseball bat it makes it a little harder to rotate than just a foam roller would be. This is really easy to rotate, and it's a little lighter too, right? This would be much easier if I set this up as a baseball bat and I made the end really skinny. It would actually be harder to rotate, even if it weighed the same. So rotating inertia or moment of inertia describes how hard or easy it is to rotate something, right? And the way we figure that out is we need to add up all the mass of the object. That's what this it looks like an E. That means sum, all right? That just means sum or add up all the mass and multiply it by the radius. And if radius is kind of weird, remember that a radius is just a line from the center of a circle, right? And so these arrows that are here, these distances, D, that's radius of rotation, right? These are all the same thing as on a circle. They're far from an axis point. And hopefully that makes sense. That is moment of inertia or rotating inertia. So then we take a baseball bat and we start talking about, well, what happens if we put a weight on it? Like baseball, softball players might put a weight on the bat for training purposes or for warm-up, right? So which of these is harder to swing? Well, we know that the equation for moment of inertia, I equals m times r squared. Put a little I equals m times r squared. That little up arrow means an exponent or time, or r squared, right? I equals mr squared. So which of these bats is harder to swing? Well, their mass is the same, and we can assume that the donut, the weight that's been put on the bat, is the exact same. Which one is harder to swing? If all the mass is the same, and we know that the axis of rotation is down towards the bottom of the handle, then we know that the one that's harder to swing is the one that's further away, and that would be A. That would be the one at the top. That would be harder to swing. It has a higher moment of inertia, or I, in my equation. It has a higher moment of inertia, meaning it's harder to rotate in a circle. Oh, come on. There we go. Sorry about that. All right. So our next concept that we're going to talk about is radius of gyration, right? What is radius of gyration? It's the exact same thing as moment of inertia. I equals mk squared. That's the same thing as I equals mr squared, right? The reason that we use this k, it's a distance, it's a radii or a radius that we measure on the human body. Gyration means rotation. So really what we're doing is we're taking the equation and now we're applying it to the human body. If I ask you about I equals mk squared, I'll make it really obvious that it's the exact same thing as I equals mr squared. So just to make sure, I equals mr squared, it is the same thing as I equals mk. One day I'll find it. There it is. All right, these things are the same as one another, okay? All right. So what does this all mean? Why do we even care, right? So now we have this guy right here, right? And what does all this mean? These are all these Ks. All these Ks, just remember I equals m times r. Let's do r and squared. All right. I equals mr squared, or I equals mk squared. K and R are the same thing, radius of gyration. A radius is a radius. It's just a line from a center of rotation. So what is this slide telling me? Well, it's actually something really important. What it's telling me is that we can alter how easy or hard it is to rotate different parts of our body around a joint. And in this instance, we're talking about the hip. Everything is coming from the hip. You can see that, right? So let's go ahead and think about it for a second. And you guys can do this with me if you want. So if you're standing, right, or you're running or you're walking, would it be easier to walk with straight legs or to pick up your leg and move it like you normally do? The second one, right? So when we're talking about rotation at the hip, could be any joint, but right now we're talking about rotation at the hip. We're talking about that. You have to consider that I equals mr squared, I equals mk squared, same thing. The mass isn't changing. The mass on your leg, ooh, smooth. The mass on your leg isn't going to change, all right? So that stays the same. So the thing that we have control over is the radii. So if we're looking at the distribution of mass, and I know on my leg I have a lot of distribution of mass, right? We look at the distribution of mass, and we think about how far away the mass is from the center of rotation. This is my center of rotation at my hip. How far away is all the mass from the center of rotation? Well, if my leg is straight out, right? If it's straight out, it's really far away from the center of rotation. So I'm not going to be able to rotate around my hip as efficiently as if I bring my heel up to my butt. Yeah, right? That's a lot easier. So you should think about that in terms of human movement. That's a big reason why we have so much range of motion at our joints, so that we can bring the radii, we can make the radii or the R smaller. The mass isn't going to change, but we can modify the I, or moment of inertia, to make it easier to rotate. If I want to rotate easier, if the hip is up here, I'm going to bring my heel as close to my butt as possible. That way I can swing around my hip a lot easier than if I was walking straight-legged. If you ever want to see how hard it is to walk with straight legs, go power walking, right? Go once the coronavirus is over, or if you're watching this right now and it's been over for a long time, go take grandma and grandpa and go do some power walking, right? It's really hard because you're keeping your legs pretty straight the entire time. So then we start talking about runners, in particularly, are a really good example of how important the radius of gyration, or the radius of rotation, and moment of inertia is. How easy is it to rotate around a fixed point? In this instance, we're talking about a fixed point is our hip, right? And if we want to rotate around that hip quickly, we bring the heel up to the butt. And when you watch really good runners, really elite runners, sprinters or endurance athletes, they are going to bring their heels up towards their butt before they swing their knee through. It just makes it easier to rotate at the hip, more efficient, so they're using less energy, right, to do the same amount of work. Now, what about on the opposite end of the spectrum, right? If we're talking about muscular strength, that's the ability to produce torque at a joint. So remember, look, if we're thinking about torque, right? If we're thinking about torque, remember torque has to do with rotational force, right? So if I'm producing rotational force, Newton meters, right? That all depends on how much muscular strength I have, right? And if the axis of rotation is really close to the joint or really far away from the joint, that's going to have an impact on how easy it is to rotate the joint, or to stabilize the joint. Okay, so if I have a weight, right, on my wrist and it's pulling me down, okay, that's making the moment of inertia tougher on my joint. So how strong am I to be able to resist that rotation now? So moment of inertia goes both ways. We can, if we increase the mass or we increase the radius of rotation, or we decrease either, we're going to make it easier or harder to rotate. And muscular force or muscular strength is what's going to dictate our ability to actually move the joint, depending on how far away the mass is distributed from the center of rotation. All right, so for those of you who have ever belly flopped off a diving board, this one is for you. So now we've talked about moment of inertia, and we're talking about rotating around an axis. So we're going to use the whole human body in this example. So how is the human body rotating? Well, first you have to pick which axes they're rotating around, and those could be your primary anatomical axes, right? Could be your vertical. It could be your sagittal axis. It could be your frontal axis. Medial, lateral, anterior, posterior. They have all different types of names for them. We're not going to worry about that. It's easy to kind of just draw how someone would be rotating, right? And in this instance, we're talking about flipping, right? Or rolling in the air. And moment of inertia has a lot to do with that. And I should say this too, if we know what the axis of rotation is, usually it runs through our center of gravity, right? So if we spread out and we spread out our mass, like in the picture to the very, very right, if you spread out your mass quite a bit, that makes the R, I equals mr squared, right? So hopefully this makes sense. Probably not. That looks like crap. Let's not do that. Sorry, guys. I equals mr squared. If you look at the picture on your slide there to the very right, the R would be very high, really high R, because we're really spread out. So the length of the radii from my wrist, my hands, all the way to my center of gravity is really long. So this person is not going to rotate as fast as the person next to him with his hands down at the sides, right? That's important to understand that the guy in the very middle that's tucked into a tight ball, radius is really small. Radius is really, really small. Mass hasn't changed, right? Because this is the same dude. So mass hasn't changed. So he's going to spin really, really fast. And then when he opens his body back up or he uncurls his body, he's going to slow down because if we're assuming he's flipping in the air, when he starts to uncurl from the ball, his moment of inertia, or the I, starts to get harder, right? Or starts to go up. And the higher your I is, the harder it is for you to rotate. Moment of inertia is measured in kilograms per meter squared. I still don't think you'll be able to see this. Just remember kilograms per meter squared, all right? Okay, so we talked about, now we know about inertia, moment of inertia. How easy or hard is it for an object or something to rotate around a fixed point? Okay, so now we're going to talk about angular momentum. So we talked about angular momentum, or we talked about momentum linearly, right? It's a force times time equals change in momentum. So that impulse, however much, if we apply a force really fast, we're going to get a ton of momentum. It's the quantity of movement, or quantity of forward motion, I should say. Quantity of forward motion, that's momentum. Now we're just talking about momentum as it's swinging, right? So if I got an old jump rope here and I start swinging it, right? This has momentum, right? It's moving around a fixed point and it has momentum. Angular momentum, the quantity of its ability to continue swinging in the air is momentum. And we're going to talk about angular momentum. So how do we measure angular momentum? Well, we use that moment of inertia. First things first, moment of inertia. How easy or hard is it for something to rotate around a fixed point? And that we know that's I, right? Angular momentum, we use the letter H. And what we do is we take I and we multiply it by angular velocity. That is a kinematic quantity that we learned about in our last chapter, right? So if we remember, W equals angle equals change. I'm going to put change in angle over time. All right. I can't put a Greek letter in there. So hopefully that makes sense, and that's a good reminder. So if we look at the angular velocity, how quickly something is moving at an angle, how quickly it's moving at an angle, we multiply that by the amount of inertia that it has, how easily or hard it is for it to move in an angular or a path around a circle. That's going to describe angular momentum, right? As mass or angular velocity increases, angular momentum increases proportionally, right? And we know that because mass is a part of, so we have two equations here. Sorry, guys. If we think about, I equals mass times radius squared. Right? So those are the two equations that if we look at H equals I equals M times R squared, right? So you have to understand that when we look at angular momentum, it's comprised of really two equations. So we have angular velocity is the change in angle divided by time, and then we have mass times radius squared is I. So there are factors that can influence how much momentum something has, right? If the distribution of mass with the respect to the axis of rotation, right? So if you have a set amount of mass and it's further or closer to the axis of rotation, that is, we can see that's R, right? That's R. So if something is really far away, that's going to decrease its momentum. That's either being out here or being in a ball. My mass isn't changing, but right now, if I want to spin faster in the air off a diving board, I'm going to crunch myself into a ball. My mass didn't change. But my R went down and my I went up, right? And that would increase my angular momentum. Now this slide can be a little confusing, but really what it's telling us is it's taking all of the different parts of the body, and telling us that angular momentum of a swinging leg is the sum of all the different swinging parts. I'm not going to come back to this probably after this slide at all. Just understand that the human body is a linked chain. It's a kinetic chain. It's got all sorts of joints that are linked together. So if we want to know what the actual momentum of a swinging leg is, we have to add up all the moments of inertia, right, of the point that's closest to the hip, the angular velocities. We have to know the masses. We have to know the radii, and we have to know the angular velocity of the radii itself. And we have to add all those together. And if we get those, we know what the momentum of the entire swinging leg is. So the kind of the point of this is that the human body is pretty unique and really intricate. I'm not going to have you do this in class. It's just kind of interesting, kind of cool. Okay, so what is the principle of conservation of angular momentum? this is kind of like what we talked about when we talked about conservation of energy, potential energy, and kinetic energy. When gravity is the only thing acting on something, angular momentum is conserved. That is when something's in the air. So when something's in the air, angular momentum is conserved. The total angular momentum of a given system, a system could be somebody flying in the air doing flips, right? It remains constant. Newton's third law, in the air, reaction force comes from the kinetic chain. The kinetic chain means us. The kinetic chain is the link of muscles and bone. So the only thing that you can do in the air is you can change how your spinning body looks, or you can manipulate your position. You are not going to manipulate your momentum. You're not going to slow it down or speed it up. It's always going to be the same. But because there's two components to it, moment of inertia and velocity, you can change. So if, if we know that H equals I times W, right? So those play off of one another, right? If this is I, right, or a moment of inertia, how easy or hard is it for a body to rotate, right? How easy or hard is it to rotate around a fixed point? And this is omega, or W, right? Angular velocity, right? And we know that when somebody jumps and is flipping through the air, right, and they're in it, the H is going to be constant. H will not change. So if I goes up, W must drop, or omega, velocity. So if moment of inertia goes up, angular velocity must go down, and H stays the same. Or if we start spinning faster, that must be because moment of inertia has started to drop. And it means it's easier for me to spin in the air, right? And H has stayed the same. Momentum is never lost, right? It stays the same. But the way it looks, are we spinning faster or slower, or is it easier or harder for us to spin? And remember, I has to do with mass, which doesn't usually change. That's not changing. And so really the biggest thing that affects I, or moment of inertia, is the radius. Are we tucked into a ball tight? Do we have our arms in tight with a really small radius, so we spin faster, greater angular velocity? Or are we spread out in the air? We have really long R, right? Really long radius of gyration, really long. So that makes the I greater, and that drops angular velocity, and we slow down spinning in the air. Okay, so what about something like a volleyball spike? During an airborne execution of a spike in volleyball, angular momentum is never lost. It just changes, right? So I, moment of inertia, times omega, or angular velocity. So it doesn't change. So how do we conserve angular momentum in midair, right? Everything has to be balanced. And in this situation, remember, she's rotating around her center of gravity. So she's rotating. So if I go to spike a volleyball and momentum wasn't conserved, if I go to spike a volleyball and I rotate my arm around, right? What my body wants to do is it wants to start rotating forward. And because I'm in midair, there's nothing that's affecting my flight other than gravity. So when I go ahead and I spike the volleyball, if momentum wasn't conserved, then I would just flip forward in the air. Thankfully, momentum is always conserved, and your body does it automatically without you thinking. In order for a volleyball player to stay upright in the air when they swing their arm, right, they rotate their lower body forward as well. So if I'm in the air, I know you guys really want to see me spike a volleyball, right? If I'm in the air and I throw my arm forward, it's going to want to make me rotate. So what do? I kick my legs forward, which sends me back the opposite direction, and everything balances out. If I didn't do that, right, and for a moment, I know this is weird, but if you think about someone who didn't have a lower body and they threw their arm, right, forward, they would start to rotate forward pretty quickly. So in order for your body to conserve angular momentum, right, in order for H to stay the same, your body balances it out naturally. So you throw that arm forward and you spike it, and your body wants to rotate forward initially, but it won't, because as you do that, you're going to kind of throw your legs into a pike position forward, and H is going to stay the same, right? So you balanced it out. So why don't we look at somebody spinning in the air? This is actually a really, I like this example. When angular momentum is conserved, changes in body configuration produce a trade-off, right? So it's a trade-off, right? That's what I was saying earlier. Okay, so again, if my green marker is moment of inertia, right? If my green marker is moment of inertia, and my red marker is, well, actually, let's do what's on the screen here, okay? All right, let's do what's on the screen. Okay, so angular velocity, moment of inertia. Remember, I'm going to put it on here for you guys. Text I equals m times r squared, okay? So I equals m times r squared. The mass isn't changing. Whoever this person is doing this flip on this slide, their mass isn't changing in the air, okay? So, and it says angular momentum, it uses an L in that equation. Don't pay attention to that. We're using H, okay? That's what your book uses. So, as someone starts to jump off the diving board or whatever it is, their moment of inertia is pretty high because they're pretty spread out. Then they start to tuck themselves into a ball. They start to come into a ball, right? And R starts to go down. Mass isn't changing, but R starts to go down, which starts to make I, right? It starts to, so we started here. Our moment of inertia was high. Our angular velocity, we're not really spinning that quickly. But then we start to tuck ourselves into a ball. R goes down. I goes down. Angular velocity starts to go up. We start to spin really quickly. We're spinning in the air. We're spinning in the air. And then we start to spread our body out again. And R starts to get bigger, which makes I bigger. And we start to slow down, right? And the entire time, angular momentum was conserved, meaning H stayed the same. It's just this trade-off between angular velocity and moment of inertia. So in diving in particular, right, that's where these people become really elite athletes. And what they can do is they can manipulate their body position in midair. Angular momentum is never changed, right? But they can manipulate their body in mid-air into different positions, and they can manipulate their moment of inertia and their angular velocity to get them into the positions that they need to be in to score well in the dive. So a skillful human performer can rotate 180 degrees or more in the air with zero angular momentum. Because in a pike position, there's a large difference between radii of gyration for the upper and lower extremities. This is actually really cool. So in a piked position, like this person is in, they're actually, there's zero angular momentum, right? Which is kind of cool. They float in the air, basically. They're not rotating. So they go into this piked position, and if you look at the way where their center of gravity would be, is literally right where the cross is. And they float in that position for a half second, and then they flip themselves 180 degrees, right? Because in that piked position, they're basically like the balanced foam roller around their center of gravity, right? They float, and then they flip themselves 180 degrees, and momentum is still the same. It hasn't changed. They can just manipulate their body in the air with so many quick muscle contractions and get themselves into 180 degrees around the other direction. Pretty cool. So how do we change our angular momentum, right? How do we, I should say, how do we produce angular momentum, right? How do we actually get angular momentum to begin with? How do we get this quantity of movement? Well, it's the exact same as linear momentum. It's an impulse, right? And it's torque over time, right? Torque times time. Sorry, not over time. Torque times time. So the amount of rotational force we apply in the amount of time that we apply it will give us a change in momentum, right? From a place where we didn't have momentum to begin with, right? Once we're in the air, right? Once we're in the air, we created the impulse already. And it's easier to describe things that are in the air, but you don't have to be. But when something is swinging, right, we've created a torque already. And remember, let's try this again. I think my blue marker might be better. So if we remember that torque, right? Torque is just how much force are we applying away from a set point of rotation, and how far away is that point of force, right? Newtons times meters. So this is torque. You might want to review that a little bit from a couple of chapters ago. That is torque, right? So, and that makes a lot of sense when we think about the joints of the body, right? Because we had that all over our first test. Torque is just applying force to attachments. So from one end of a joint to another. So we can create this angular impulse, right? We can create this angular impulse, this torque in a certain amount of time. And if I really wanted to, let's say if I want to throw a baseball, right? If I want to throw a baseball, right? My triceps attach here, and they attach here, right? And I want to create a lot of momentum, right? I'm going to snap it out there really, really fast. So I have to have a lot of muscular power, right? And I need to create a lot of torque. I need to create a lot of torque at this attachment. I need to pull it really quickly in a short amount of time to create a lot of angular momentum, right? And that's how would I make that more difficult? What about if I put a weight around my wrist right here? Well, I'm not going to be able to, I can apply all the torque that I want, but it's going to slow things down. My angular momentum is going to drop. So angular impulse, how much torque do we apply and how much time? That creates momentum. And remember, momentum is described as those two factors that play off of one another, angular velocity, or omega, and moment of inertia, and I. So angular impulse is really what allows us to spin faster, all right, especially off like a diving board, right? So when we start to talk about like spinning and going off of a diving board, one of the things you have to think about is, okay, in a diving board in particular, right, that you're applying force into the diving board, it's applying force back up on you, and how far away are you from that force? Remember, reaction force is going to come back up off of the diving board. So how far are you away from that force? See, it's perpendicular to your center of gravity. So if you apply a big force, right, and you apply a lot of torque in a short amount of time, which that diving board is going to put torque onto you, it's actually going to rotate you as a body, as a whole. You're going to spin really, really fast. Angular momentum. Now, once you're in the air, your angular momentum is there, right? The only thing you can do is you can change how it looks. You can spread out and you can slow your spin down, or you can tuck into a ball and speed up your spin. More angular velocity or more moment of inertia, or less of either or, right? But the initial amount of spin that you have, or angular momentum, is really dictated by the impulse that you get. And that doesn't have to be off a diving board. That can just be from a back flip or a front flip you do off of the ground, right? You do one too slow, you might land on your neck. Ouch. So what can we do to get ourselves a better takeoff or a better impulse? Swing your arms. Okay, swing your arms. The arm swing during the takeoff contributes significantly. Doesn't matter if we're on video or not. The arm swing contributes significantly to angular momentum buildup. It can get you a greater amount of impulse. So again, applying torque in a certain amount of time. Well, remember, torque is rotational force. So how can we apply rotational force? We can swing our arms. We can apply more torque. We can apply more force into the diving board. It applies more force back on us, which creates more torque on our body, because it's basically shooting our feet out from underneath of us, and it rotates us faster. Okay, so now we're going to talk about angular momentum during the takeoff of basically a spin in the air with a ballet dancer, or even an ice skater. So the reaction force, or how much torque can be applied with the foot. If the foot's in contact with the ground, applying a certain amount of torque when you rotate is actually going to dictate the impulse that you get to start spinning yourself, which is pretty cool. Surface reaction force. What is that? Okay, surface reaction force just means we have contact with the ground, right? If this is my foot, I have a foot, right? I have a foot in contact with the ground, right? And you can, in order to spin yourself, what you do when you spin yourself, you can try it, right? When you spin yourself, you're going to have to have friction between you and your foot and your shoe, or whatever you're saying. You rotate and you create a lot of torque. And that torque, if you do it really quickly, will create an impulse, and it will allow you to spin and gain angular momentum. So in the last chapter, what we did is we talked about some relationships between angular and linear quantities, right? I'm going to move my video out of the way here if I can. If we're talking about mass, right, and we're talking about quantities, moment of inertia angularly, mass linearly, and then there's other relationships here. Obviously, momentum in linear terms, mass times velocity, same exact thing, right? Same exact thing in angular momentum. It's just mass times how far away it is, mr squared. You can see they're using the mk squared here. That's okay. It could be mr squared as well. Angular impulse is torque times time, or force perpendicular to something and the amount of time. That's force and perpendicular distance, or FD with a little perpendicular sign. That's torque. Same thing, right? So you can't apply torque to something parallel, right? This would be parallel. This would be perpendicular. A T is perpendicular. So in order for something to have torque, you have to rotate it like this. You have to be able to come at it perpendicular, right? That's what that means. Linearly, impulse is just force times time, straight ahead. Same thing with torque, right? It's just straight line pushing force, not rotating force. Angularly, torque is force times the perpendicular distance that's rotating it, all right? So what is the angular law of inertia? A rotating body will maintain a state of constant rotational motion unless acted on by an external torque. So this is one of Newton's laws. Everything will remain rotating unless something affects it. Air resistance is one of those things. So let's go ahead and talk about that. All right, so what is the angular law of reaction? So a net torque produces angular acceleration. Let me move myself out of the way here. For every angular action, there's an equal and opposite angular reaction, right? That should hopefully make sense. That's one of Newton's laws. For every action, there's an equal and opposite reaction. So as far as angular acceleration, right, which is alpha, so if we take a look at translation of Newton's second law, force equals mass times acceleration. How would we look at that angularly, right? We just change it into angular terms, all right? Torque, or a force over a certain distance, F times D. I'm not a super big fan of that interpretation of it. I really like torque equals moment of inertia. So torque, a rotating force, T, a rotating force, equals I, angular moment of inertia. Torque equals moment of inertia times acceleration, right? So if we want to rotate something, or we want to apply rotating force, right? And this is the same thing as saying force equals mass times acceleration, right? It's just now we're using angular terminology. Force, pushing something straight ahead, is the exact same thing as rotational torque, right? They're just angular versus linear. And then moment of inertia is the mass. It has to do with the composition of the mass and how far away it is from the axis of rotation. And then acceleration is angular acceleration. Is change in angular velocity over time. So for every action, there is an equal and opposite reaction. If we apply an angular torque on something, there will be an angular torque applied back on us. All right, and so what your book describes is, and you can think of it this way: baseball player. Swing a bat in outer space where your feet aren't on the ground at all and there's no gravity at all. What would happen? You swing the bat and your whole body would continue to rotate. if you apply a torque to your upper body and start rotating, your lower body is going to follow, right? Well, here on Earth, where we have gravity that roots us to the ground and we have feet that claw into the ground, especially if you're wearing cleats, that doesn't happen. We can rotate our upper body and our lower body actually starts to rotate, but it applies a torque one way, and then our cleats grab onto the ground and it applies an opposite torque. So we can actually, if this is my hips, if my upper body is rotating, my hips can actually stay pretty stable. Or I can dig into the ground and rotate my hips too to get a really powerful swing, right? So remember, the nice thing about living on planet Earth is we have the ground to contact. So if we want to rotate and keep other parts of our body stable, we can do that because we have contact with the ground. And we start to rotate, but that applies a rotating torque in one direction, which gives a torque back on us, which allows us to stay stable or able to manipulate our position better than if we're in midair. Once we're in the air, the only thing that's happening to us is we're able to spread ourselves out or crunch ourselves into a ball, and that will decrease or increase the amount of spin we have, but it won't change the amount of force that's being applied to us in the air unless we get struck with something, which that would hurt. Okay, so when we were in kinematics, when we were talking about kinematic values, we were talking about rotating in a curve, right? And we talked about a car going in a curve. All of this applies to human joints, right? If something is swinging, I use the bicep constantly. If something is swinging around a set point, all of this applies back on the human body. So what is centripetal force? Centripetal force is a force that is directed inwards towards the inside of a circle from a rotating body. And it can be described, it is the force, it is the kinetic or force component of radial acceleration, right? Radial acceleration, we talked about that acceleration that's going in towards the inside of the circle, right? Let's use, so remember radial acceleration, right? Goes inwards, and then we have tangential acceleration or just straight line acceleration. We talked about that in the linear angular kinetics in the last chapter, right? So then we have another thing that we have to consider is that we were talking about acceleration there, kinematic value. Then we have to think about the amount of force that has to be applied in towards the inside of the circle in order to keep something rotating around a fixed point. Lost my mouse. I got it back. Okay. How do we describe centripetal force? How do we describe it? There's two ways we can describe it. We can describe it using a linear way. So if we take the amount of mass and we look at the straight line velocity, how much mass do we have and how quickly is it moving forward in a straight line? And we think about how far away it is from the center of the circle, that quantity, mass times velocity, divided by how far away it is from the center of the circle, it's going to dictate how much force has to be applied inward to keep us on a curved path, right? Again, you cannot move in a circle. You can't move in a circle. You can't rotate something in a circle without that object being pulled inwards constantly to keep it on a curved path. And that's what centripetal force is. You have centripetal acceleration. It's accelerating inwards towards the inside of the circle while it's also traveling in a straight line, two parts of the same thing. Another way to describe centripetal force is the amount of mass something has, how far away it is, mass times how far away it is, and how quickly it's rotating, or angular velocity. So you can see that there are two different ways to describe centripetal force. And really, the biggest takeaway is just realize that there has to be a force applied inwards towards the inside of the circle to keep us on a curved path. So we're going to come back to another example of someone on a curved path. You have to lean into the curve, right? Okay, so here's the deal. If I'm running, right, and I'm running and I'm going around a curve, I have to lean, right? Okay, why is that? Well, first of all, I have to apply friction. I have to apply friction to the ground, which creates a reaction force, which is actually centripetal force. So that's the center of the circle. I'm running and I'm going around the track and I'm leaning. Well, I have to lean, one, because I have to apply centripetal force. I have to get inwards because I want to go around a curve, right? I'm going around a curve. I'm going around a curve. But what happens when someone is running on a curve? Centripetal force pulls that person inwards. And imagine you're on a rug and somebody pulls the rug out from underneath you. Well, that's a torque that's being applied at your feet. That's if centripetal force is pulling you inwards, right? It's going to want to scoot your feet out. You're going to tip over. It's this balancing act, all right? Centripetal force, in order to keep ourselves on a circle, we have to apply a force in towards the circle. But that force because it's applying a force at our feet, it wants to yank us like a rug being pulled out from underneath us. It's going to tip us over. So what do we do to balance that out? We lean, right? So that way we keep centripetal force. We keep force in towards the circle so we can stay on a curve, and we lean so that we don't fall over the opposite direction. If you've ever watched a race car go around a circle and it loses friction on the tires, it flies right off the track, right? Because it's lost that balance between centripetal force and the leaning and the torque. It's a kind of hard concept to understand, but we will talk about it more so that it makes sense. Here, I don't want you to pay too much attention. I should take this equation off the bottom here. It can be confusing, right? The points of contact on a cyclist who's leaning around a curve, you can describe those points of contact a couple different ways. The big thing that I want you to take away here is what I just talked about, is this cyclist has to lean inwards, right? If we look at all the forces that are being applied here, this cyclist has to lean inwards. Why? Because in order to stay on a curve, there has to be centripetal force that goes in towards the inside of the circle. And if you're applying force in, every action has an opposite and equal reaction. You're going to have force applying out. So you're going to want to tip over. In order not to tip over, you have to lean inwards. So here are a couple practice problems that I want you to work out on your own. Why do hamstring injuries occur at such high rates in elite sprinters? How would you explore this question with concepts we have learned in this section? It has to do with rotational forces at joints and the structure of the hamstring itself. It's actually pretty interesting. So think about that. That could be a good test question, and we can discuss that in lab this week or in person. Never mind. Here's the answer. Forgot that was on here. My bad. When you run, the femur rotation around the hip, it creates a whip, right? It creates a whip, and it whips the tibia and the fibula, or the lower leg, around the knee and around the hip. and it creates a huge amount of impulse, a huge amount of rotational force and an impulse. So here is the actual practice problem. All right. And I would like you to do this on your own and try this out. This can give you an idea of how big that force that's created when the leg whips out, and why we might actually get a lot of hamstring injuries if our hamstrings aren't well developed. That's the end of the slideshow. Be a good idea to write down any questions so we can discuss them later in the week. Have a good one.